Welcome back to CS596. Okay, so today we will continue we'll finish up the remaining parts for the word embedding chapter. So last time we stopped here when we introduced negative sampling as an alternative way to train a word embedding a word to vec model instead of the softmax output. Okay.
Hi, Professor. I have a quick question. Comment. I tried to upload the homework, and I can only upload one file. It won't let
Okay.
me upload both uh,
Uh,
notebooks.
do you mean for this which homework? The
Assignment 8.
assignment 8 for RN. All right. I will double check. So I don't know why I didn't restrict the submission type. So what does the website, what does Canvas say when you upload the?
So when I go to choose file, I click on the first file, and then when I try to click add file, it
Uh-huh.
won't pop up for me. It's grayed out.
Okay. Um, you didn't have this issue when you submit for the convolutional neural network assignments.
No, I could try again, but yeah, last night it wasn't working for me.
Yeah. Ryan said you need to click the add file. So maybe you can try again and I will double check to see if I had any difference from the last assignment.
Okay, thank
Yeah.
you.
Yeah. All right. Thank you. Okay. All right. Let's go back to the slide. So in the softmax outputs, you basically need to you need to output the probabilities for all possible words that exist in your vocabulary, which is a lot of computation, right? If you have 10,000 words, then you need to output the probabilities for that many 10,000 possible words. So that's a lot of computation. So, and it's not necessary to use these complete probabilities for all the vocabularies to train the word-to-vec model. And there are two alternatives, which is hierarchical softmax and the negative sampling. So in practice, negative sampling is easier to implement and easier to easier to understand. Okay, so the thoughts of negative sampling is that we do not need to estimate the probabilities for all possible words in the vocabulary, but instead we can just given a context, we can just choose to predict if a random word is a target or not. Okay, so if a word appears within a certain window of a context word, then it is a target word. Otherwise, it is not. Say, in this case, the context word is orange because the juice appears within a fixed window. Say, if we assume that the window is 5, like 5 words to the left and 5 words to the right of orange, then juice is within that window, then the label for the target word juice is 1 because it is indeed the target word. Otherwise, if you choose, like if we randomly select the word king, and of course it is not the target word because it is not even in this sentence, right? For the other very common word, the, so it is a very common word, but it is not in this sentence. So the label for the word the is also 0. Okay. So we basically need to the first step of conducting negative sampling is to pick an actual target word from the window, right? Given a context word, then we can always choose a target word from the window. Like this serves as the positive example because this is a real case, not a fake case, real data points. And the second step is to randomly pick a constant number of words, say k words, from the vocabulary that are not in the window. Okay, and these serve as the negative examples. Okay, the positive example has the positive label, and the negative examples have the zeros labels. And we use all these pairs, word pairs, as our training data sets. And we have the the labels available as well. So given these pairs of words as our training data, we can, instead of using softmax to estimate the probabilities for the target word, so here the t, lowercase t is for the target word, and the lowercase c is for the context word. So we can actually use a logistic regression to replace the softmax, because our label just becomes 0 or 1, given the pairs, given the context word and target word pairs. And the logistic regression, for the logistic regression model, the output is the sigmoid function, right? And the input to sigmoid function is the dot product between the target word and the context word. So these, in this case, the target word here doesn't need to iterate over all possible words within the vocabulary, but it's just within the current positive example and the negative samples. It is within the current kind of mini batch. Okay, and this is of course an approximation to the softmax method, but this approximation can already provide a very close performance to softmax, and it brings tremendous improvements in training speed. If it's a softmax function used here, then the training speed for a word embedding model, for a word-to-vec model, is extremely slow. All right. Okay, so let's look at the mathematical equations here. Remember that we use the big O to indicate the one-hot encoding for the word orange, and if we use the embedding matrix E times big O, it gives us the embedding matrix for orange. So this time the output layer is not all possible words in the vocabulary, but instead it's just k+1 logistic regression output, because we assume that we just need to sample one positive example and k negative examples. So in total, it is just a k+1 output, which has the logistic regression output unit. Okay, and these output units estimate the probabilities for both the target word and the negative samples. Okay, so this is significantly faster to compute than the softmax. And the technical detail is that the k negative examples are different in each training iteration. So when you go through when you iterate over the training data sets, you basically go through each word and you examine the left context and right context given one context word. So you basically need to sample different a different set of words each time when you go through each context word. Let's see what the, yeah, so a common choice for the value of k depends on the data sets. Usually speaking, when you have large data sets, then you can use a smaller k, but for smaller data sets, you basically want a larger k. All right. So let's talk about the intuitions, or like basically why negative sampling would work. The idea of word-to-vec is that we use the co-occurrence relationship to model the semantic meanings of words. Okay, so actually the embedding vectors learned for each word actually is encoded with such co-occurrence or co-location relationship between words, and the embeddings actually know which words actually reflect which words tend to appear together within a context window and which do not. So if the two words, they have more close semantic meanings, which means the word vectors, they are closer in the embedding space, then that indicates these two words have a tendency to are more likely to appear in the same window. Okay, because the assumption is that the similar words, or the words that have similar meanings, tend to appear within the same context. Okay, so this is a very simple philosophy taken by the word embeddings models, which is basically semantics can be described by the word's occurrence, and but also the raw inputs or the original the raw implementation or the original word embedding or word-to-vec based model is kind of has its own limits. For example, it's hard to distinguish synonymous or antonyms names. So these, because for example, like the word green and red, right? These two colors, they are more likely to appear in the same context because they are both colors, but it fails to recognize that, okay, these two colors may point to different directions. Maybe they are very two contrasted colors, like other antonyms like bad or good, because these are all very commonly used adjectives which are used in similar context, but simple word embedding models cannot capture the opposite directions of the antonyms. So a more advanced techniques or tricks will need to be used in learning the opposite semantic word meanings by using word embedding models. I think it is still a very active research area in NLP. All right, we are basically done with the word-to-vec as an example to show how word embeddings are learned, but that is not the only way to learn word embeddings. The term word embeddings is a more general term which refers to the technique to use distributed representations to encode the meanings of words. And the word-to-vec is not the only way. And a very famous example is the global vectors, which is a different method than word-to-vec, but also learns very expressive word vectors in a different way. So this paper came out the next year after word-to-vec was proposed in 2013. So in the paper, they actually draw very interesting connections to the word-to-vec paper, and they also explains why some of the hyperparameters needs to be set in those particular ways in the word-to-vec. And the idea is quite straightforward. So these GloVe methods or global vectors model, it proposed to minimize the cost function, which takes into consideration not just the similarity between words. For example, if you look at the sigma operator here. This means we iterate over all possible pairs of words within the vocabulary. The V is for vocabulary size. So the I and J iterates from 1 and ends up to V, which means we examine all possible pairs of combination, pairs of words, okay? And this here, it looks familiar, it is the lowercase e is the embedding parameters or the embedding vectors from the embedding matrix. Okay, so this is embedding matrix for I and the embedding matrix for J. So the dot product between the vector for I and the vector for J is actually the kind of measures the similarity between word I and word J. Right? It is the dot product, and dot product is the main components of the cosine similarity, right? Basically, the dot product between two vectors can be used to measure how much these, how similar these two vectors are. Okay, so basically, we want to minimize the cost function, but this dot products is accompanied with this quite strange term, which is the logarithm of xij. And here, the xij is the count of times that word I and j appear together. Okay, so, and there's a negative symbol before it. So, which means because we want to minimize the cost, the whole j is minimized. And the negative terms means that we want to kind of maximize the xij, which is the count of times that word I and the j appear together. So this actually conforms with the principle that we showed in the previous slide, that we assume that the words that appear together more often, they tend to have more similar meanings, right? So if the xij is very big, then which means if we want to minimize the costs, then the inner product, the inner dot products of between the two vectors also need to be big, right? So that the difference is becomes much smaller, right? And for the pairs of words that don't have a very large xij, then the inner product can be a very small value, which indicates that they are pretty farther away in this embedding space. So this is a very, I think it's a very intuitive explanation for why such a cost function is used in GloVe. And it turns out that the GloVe vectors is very successful, and it's often draws very similar performance in a very broad range of NLP tasks. And even still nowadays, people will use GloVe vectors and word-to-vec vectors in basically a interchangeable style. Like they all, I assume they have, people assume that they have pretty similar performances. All right, so that's a piece of information about GloVe. Okay, so I have a few slides left. So in these slides, let's see how the word embeddings are evaluated. So I will introduce the so-called intrinsic evaluation here. So this type of evaluation basically looks at the quality of embeddings using the word semantic similarity task. Okay, so basically we need to first, each row, so this is a table, right? Each row contains one instance, and each column, the first column is the first word, the second column is the second word, and we need to compare the two a pair of words. So for example, the first row is book and library, and of course book and library, they are kind of related to each other. So the third column is the scores obtained from human subjects. So this column is like obtained from human subject experiments. We ask students or other human subjects to rate how likely or how related each pair of word is, and they are asked to give a score between the range of, I think it's between a range of 0 and 10. So this third column is fixed. Okay, so then after a word embedding model is trained, then we will have the vectors for book and the vectors for library. Then it's easy to compute the cosine distance between the two vectors. And this is the score resulting from the cosine distance computation, D1, right? So then we have the fourth column, which is the cosine distance column. So then we can simply use the correlation between the green column, the fourth column, and the third column, the human score column, as a metric to measure how good the word embeddings are, right? So in theory, we want the cosine distance to be as close to the human scores as possible, right? We want the embedding models to be human-like, to understand, to capture the actual semantic similarities, right? So then we will use the Spearman's correlation between these two columns to indicate the quality of the word embeddings. Basically, we want a higher score in Spearman's correlation. So that is one type of intrinsic evaluation for word embedding models. Okay, we have 2 slides left. Here, I showed part of the examples of how we can basically implement the PyTorch, implement a word-to-vec model using PyTorch. And PyTorch provides an easy tool to use, which is the embedding. So it provides a way to initialize an embedding matrix. So the 2 and 5 here indicates that I only have 2 words in my vocabulary, and each word is represented by a 5-dimensional embedding vector. Okay, so like if I initialize the embedding like this, and I can initialize a after I initialize the embedding object like this, within the matrix, it is just a bunch of random numbers. So I construct a lookup tensor here using the IDs of hello. Okay, so the word ID of hello is 0, right? So if I use the 0 to query the embedding matrix, it will give us the first row of the embedding matrix, which is a random vector that have 5 elements, because the embedding is initialized to a 5-dimensional vector, 5-dimensional embedding vectors. And these, as you can see, there's a gradient function here, which means these are parameters. We can use this vector to be a learnable parameter by constructing some loss function and then pass the loss to an optimizer and use the gradient descent to update these vectors. And as long as the training procedure is sufficiently long, then the embedding vectors will be updated to will converge to some meaningful vector space. So let's look at the next slide. So here is a typical implementation of a skipgram-based word-to-vec model. The SG is for skipgram, and we use the negative sampling technique. So in the code here, we basically use the NM module to define a model, right? Here, one thing I think we need to pay attention is that here we define the two embedding tables, the embedding 0 and embedding 1. So this actually corresponds to the word-to-vec model. Still remember that we have one big embedding table called E, and the second table is called the output embedding table, which is E prime. Okay, so the E prime is not what we need eventually, but it must be used in the training process, because E prime will be used to look up the context vectors and the negative vectors. So in the code here, this is in the forward function, we will need to use the word index to look up the target word embeddings. So this is the first table used. And the second, context word embeddings, is extracted from the second table, from the E prime table. And also the negative embeddings is also extracted from the negative, is also from the second table. Okay, and then the logits are computed here, which is basically the dot product, right? And also the matrix multiplication between the negative sampling. So eventually we'll need to construct the loss function by combining the positive example loss and the negative example loss. And there is a negative symbol here, which is important because we want the distance between the target word and the negative examples to be as apart as possible. So there's a negative sample here. And the summation of the two loss will be returned as the total loss. And then this returned loss will be passed to an optimizer that conducts the gradients updates automatically for us. So this is a typical implementation of skipgram model, which basically we need to implement we need to utilize two matrix tables. And what we didn't show here is how the data is constructed, right? We just assume that taken within this input data, the first column is the target word, the second column is the target word, the first column is the context word, and the remaining columns are the negative words. So these, how the data is constructed is something needs to be implemented outside the model, right? So it should be implemented within the training loop. So that is something we can refer to the original paper to help us implement. But there's tons of details included in this step, which we're not covered here in the slide here. Alrighty, so that's so much for the word embedding chapter. Let me stop recording.